let's talk a little bit more about performance charts and some specific info you need on them. You studied the charts per the assignment, getting familiar with how to use them. I want to go over a few nuances with these charts. Again, I've got a discussion page for you. International Standard Atmosphere. This is something that you have to know going into performance calculations, as this information will not be given to you. Right? Sea level. Standard temperature at sea level is 15 degrees Celsius. Now, most of you are going, duh, I already know that, got it. But a lot of pilots are forgetting that it's only at sea level. That's 15 degrees Celsius. And standard pressure is 29.92 inches of mercury. As you go up, standard temperature changes for each altitude you're at. International Standard Atmosphere, ISA. And it changes by a rate of 2 degrees Celsius colder per 1,000 feet. You also lose 1 inch of pressure per 1,000 feet. So that means here at Battle Creek, which we're approximately 1,000 feet mean sea level, our standard temperature is approximately 13 degrees. So if you're using formulas for density altitude calculations, you need to always use ISA temperature for your altitude and not just 15 degrees. So just keep that in mind. Also, the way the charts are utilizing abbreviations on it, you'll often see this ISA on there. So if you do see ISA, it's just simply saying that's the International Standard Atmosphere. It's starting at sea level at 15 degrees, and it's decreasing by 2 degrees Celsius per 1,000 feet. So the concept that if it's labeled ISA at 8,000 feet, well, obviously, at 8,000 feet, we have changed 16 degrees. We've gotten 16 degrees colder. So sea level of 15 degrees minus 16 means your ISA temperature at 8,000 is a -1. So that's probably easy to understand. But what if your chart has ISA -20 degrees? Okay. That, understand, means you're 20 degrees colder than ISA. It's not saying that my outside temperature is -20. It's saying I'm 20 degrees colder than this standard temperature at this altitude. So using 8,000 feet, that means the temperature is -21 degrees, because standard's -1, 20 degrees colder is -21. So it's important to be able to look in the correct column of particular charts that will lay out a standard column, a column that's colder than standard, another column that's warmer than standard. You're working with non-standard temperatures, you're going to need to determine the altitude you're using. Now, if you're departing a 4,000 foot airport elevation, you're using 4,000 feet. You need to find the ISA at 4,000 feet. And you also need to understand what is my current temperature at that altitude. So 4,000 feet, that's 8 degrees colder, so your standard temperature is 7 degrees. And if my outside air temperature is 14, I'm 7 degrees warmer than standard. That's going to be a key for a lot of your performance charts, finding out what is the difference between my current temperature and my standard temperature at the altitude that I'm looking at. All right, so let's try a top hat question. You'll need a calculating device of some type. Okay, my bad. My question has disappeared. Never mind. Sorry. I'll have to find that later. Okay. We will be doing some top hat questions here in a little bit here. All right, next concept with charts, cruise charts. You're often going to be asked a question about endurance and endurance with a reserve. So first of all, endurance means the total time consumed in all tanks, all fuel. You have nothing left of usable fuel. Okay? That's endurance. So when you calculate endurance, you might have an example where I have fuel, enough usable fuel for 3 hours of flying. Right? Questions from the FAA, though, are going to ask you, what is your endurance, but with a remaining reserve, VFR day or VFR night? Which means I need to land with fuel still in the tank, my 30 minutes for the day reserve or my 45 minutes for my night reserve. So if my question is asking me about VFR day reserve endurance, if my total endurance was 3 hours, then I'm landing with 30 minutes in the tank. I can fly for 2 hours and 30 minutes. Please do not think that you can fly for 3.5 hours, right? If you have an endurance of 3 hours, you can't go 3.5 hours, right? You run out of fuel at 3 hours. So don't ever add on the reserve to your endurance. You're always subtracting it off from it. So hopefully no one will get those questions wrong when we get to those on the upcoming exam. Climb calculations. We've got 2 sets of calculations to determine for climbing. The question is going to be somewhat, you're departing an altitude, airport elevation, altitude, and going up to a cruise altitude. That's going to be the question. Your charts are all based upon climbing from sea level. So if you are going to cruise at 20,000 feet, you can't just pick the line in your climb chart that says 20,000 feet, because that's going from sea level to 20,000 feet. So what we need to do is 2 sets of numbers is, first of all, well, what is the amount of time to go from sea level to 20,000 feet? In addition, we got to find what is the time fuel distance from sea level up to the airport elevation. And now it's the difference between those 2 sets of numbers that gives us the answer to the question. So go over just a quick example of this. Now we utilize an aircraft, 3,700 pounds. So from our figure, £3,700, we see that. And going from sea level to 2,000 feet, well, notice we don't have a 2,000, but we have a sea level and a 4. So that allows us to interpolate then. Just an easy interpolation this time. It's halfway in between the two. Okay. And then we do have a 20,000 foot box. So we can easily just take those numbers straight away. So it's going to be the difference in those numbers right there. Right, so getting those numbers, we find from sea level to the airport elevation, a 2-minute climb, 5 pounds of fuel, 3 nautical miles. And from sea level up to 20,000 feet, 22 minutes, 59 pounds of fuel, and 42 nautical miles. So now we just do some simple subtraction, and we can find the time is 20 minutes, 54 pounds of fuel, and 39 nautical miles. However, that's not going to be your final answer yet. Modifications may be required. Often the FAA is going to have you include one of the notes and the note was to add a certain amount of fuel for engine start, taxi, and takeoff allowance. Okay. In this case, it's 16 pounds. So keep in mind, if you are departing from an airport, you are going to be adding on whatever they note for engine start, taxi, takeoff allowance. So we still got to 20 minutes and the 39 miles, but our 54 pounds of fuel plus 16 now means our final answer is 70 pounds of fuel. So keep in mind, once you find something on particular charts, it may need modification. So you really got to read the question. Always take your time reading these performance questions. You can easily miss a key word and it changes the whole answer for you. All right, that was all standard conditions. Let's take a peek at a non-standard climb. This requires more modification to it. So we have our 20 minutes, 54 pounds, and 39 miles from the previous slide there. Those are the standard conditions. But what happens when we have non-standard temperatures? Well, first we got to figure out how many degrees above standard is our departure altitude. In this case, we'll say in our example here, we're 15 degrees above standard. Of course, we can easily find that out with departure temperature and standard temperature for our departure altitude. Okay. But 15 degrees above standard here, the chart says add 10% to your numbers for each 10 degrees Celsius above standard. So look at that carefully, that 10% in 10 degrees, that means you have a 1-to-1 ratio, which really means every time you're 1 degree Celsius above standard, you're going to add 1% on to your numbers. If you're 3 degrees warmer, then it's a 3% increase. 12% warmer, it's a 12 degrees warmer, it's a 12% increase. Keep that in mind, right? Any increase above standard temperature is an increase in performance. So then our 20 minutes with 15% becomes 23 minutes. 39 miles becomes 44.85 miles. The fuel one takes a little bit more work to do, because we have to work with that 54 pounds of fuel first. I'm telling you, this is how the FAA is coming up with their answers for this type of problem. They take the 15% on the 54 pounds. That was the climb fuel. Okay. Then they're adding the 16 pounds for the start, taxi, takeoff allowance. Don't add the 16 and then do 15%. You'll get the wrong answer. Okay. It is going to be the climb fuel plus your modifier, and add in the 16 pounds. All right. A few other things about the performance charts. Cruise performance charts. They are laid out automatically with best power numbers. Thinking, well, what do we mean by best power? Let's go back to understanding mixture. So just imagine for a moment, you're in the cockpit and there's that red handle next to the throttle. Remember, that's not the on and off of the aircraft, right? But that's probably how you're treating it. That is actually a mixture control, so that we can actually lean out the mixture. I'm betting that most of the people in this room probably only touch that at the beginning of the flight and the end of the flight, right? Some of you might do it during the flight. That's great. Okay? But for the most part, most people don't touch it. So we need to understand best power. When we do that lean assist on there, it has us reduce the mixture, setting the amount of fuel going into the engine. We hit a peak, and then we advance the mixture control, and then it tells us we've reached the best power setting. That best power has a special meaning here. So let's take a look at the diagram. Right. First term we'll talk about is stoichiometric mixture setting. And that simply means all air, all fuel is burned out of the cylinder. When you are at full rich on the mixture setting, we are giving the engine too much fuel. We're actually required to give the engine a little bit too much fuel just to make sure that it always has enough fuel. So that means when you are full rich on the mixture setting, you are burning all the air out of the cylinder and leaving fuel left over. Now that fuel does help cool the cylinder down from the inside, so it's not a bad loss. It is being used. But the amount of power that you're getting out of it is reduced. So our black line here is the amount of power. When you're too rich, you can't operate the engine. We start leaning the mixture out. We start getting this increase now in the amount of power. And we could actually hear the engine develop more power. We can see manifold rising. And that keeps going until we reach this line here called peak. That's the peak exhaust gas temperature point. Okay, so when you're doing lean assist, that's the first point you're looking for. When you do have that first peak, you're at the stoichiometric mixture setting, all air, all fuel burned out. From there, you want to push, okay? Because you notice the amount of power that we've developed has dropped off a little bit. We start adding a little bit more fuel back into the cylinder, we actually get a little bit of a rise in our power output to a certain point. Okay? And then if we keep adding more back in, we'll drop off again. So at that peak power, that's where you're at best power. And you're getting the most efficient operation of the engine for that throttle setting you're at. So if you're burning all the air out, you're leaving a little bit of fuel left over, and you have achieved best power. Now, what happens if we went to our peak EGT setting and we continue to pull on the mixture control to continue to lean it? Well, as you can expect, we'll get another amount of power to drop off from it because we're now removing fuel and we're leaving more air. We're burning all the fuel out now, but we're leaving more air behind. Engines do run hotter that way, but you're not burning as much fuel anymore. You're losing some power from it. So now you're at the best economy setting. And that's the setting where you still get a good amount of energy out of the engine, right, without overheating it. So if you're in a situation where you got to stretch out the endurance of the aircraft because you're fuel critical, you got to go to best economy to do that. So, right, so that's a review then of best power and best economy settings. This applies back to your FA charts since they are all laid out with best power. But the FA might ask you a question about what's the endurance with best economy instead. So when we look at charts, our concept here, best power mixture setting is rich of the peak exhaust gas temperature. In your Cirrus, that's about 75 degrees on the rich side. Okay? Best economy setting is your lean of the peak exhaust gas temperature. And that's about 50 degrees colder in the Cirrus. FA charts are laid out best power, and you'll note that from the conditions. Up somewhere near the top of the chart, they're going to lay it all out. These numbers were derived under certain conditions. Right? The word here, recommended lean mixture. That means best power. So that's going to be important. Right? They also might have the word lean mixture. Again, that's best power. Otherwise, for best economy, they will have a note on there that states to operate the aircraft at 6 pounds per hour leaner than the best power fuel flow setting on the chart. So whatever number you find on the chart, you subtract off 6 pounds per hour. So this is figure 12 from your book. And we notice the conditions up here, recommended lean mixture. All the numbers you get from the chart here for fuel flow, these are all best power settings. And best economy is shown now up in this box here, 6 pounds per hour leaner. Right. So read the question. The question will give you the information you need. Am I going to answer with best power usage or best economy usage? So just a couple different examples from figure 12. You can always check these numbers out with your figure book if you want, but 18,000 feet at minus 41 degrees Celsius, 2,500 RPM and 26 inches, we are best power setting 318, I'm sorry. Stand by. Figure 12. 2,500, 26 inches minus 41. We are burning 99 pounds per hour. There we go. 99 pounds per hour. Now the question tells you that our recommended lean mixture usable fuel is 318 pounds. We have 318 pounds total endurance. And we're burning it at a rate of 99 pounds per hour. So no modification is needed on that. Now the other example here is best economy. So if I took 18,000 feet on a above standard day, 2,220 inches, I'm burning 59 pounds per hour. Okay, that's best power. Okay, but now the question is stating best fuel economy usable fuel. That's where I need to modify that number, okay, and subtract off 6 pounds per hour. That's going to give me 53 pounds per hour. Best economy setting. So you got to read the question. Encourage you to always read. All right. Now I might have a top hat question. You need your figure book calculating device. All right, so our problem here is recommended lean mixture, so no modifications needed to the fuel flow. And this one, you are going to find your endurance, but allow for VFR night fuel reserve. You got 2 minutes here. Notice your temperature. So you're non-standard on your temperature. It's okay, they give you a column for it. Find your fuel flow in pounds per hour. Find total endurance. Then subtract off your night reserve. Gonna push you a little bit. Shouldn't take you 3 minutes. Should have found 99 pounds of fuel per hour as your burn rate. So looking at flight time in minutes here, right? All right, see what we got for correct answer. 148 minutes. So 99 pounds per hour. You had 318 pounds of fuel. There's no modification needed. So if you're using a manual flight computer, you set your rate to 99 pounds per hour. If you're just using calculations, 318 divided by 99, that gives you total endurance. And then just subtract off 45 minutes from it. Any questions on that? Okay. All right, try another one. Now this one, different column, different power setting, but notice in the fuel line it says best fuel economy usable fuel. So this fuel flow is going to require modification. So you're going to find the best power number from the chart, and then you're going to apply the note to modify it, and then use that number with your 344 pounds. And remember, we're allowing for VFR day reserve. All right, looks like more of you got that one right this time. So best power was 59 pounds per hour. Best economy setting is 53 pounds per hour. So you should have found 390 minutes was your endurance. Day reserve is 30 minutes. That gives us our 360. Now tolerance for exam purposes will be 6 minutes. So if you get within 6 minutes, you'll be getting the correct answer there. Questions on that one? All right, looking at another figure, figure 8. It is an interesting critter as it combines several different charts all in the same one, cruise as well as takeoff charts, or I guess graphs rather. At the bottom here is brake horsepower. Cruise lean. Cruise lean is the best economy setting. Another one is best power in level flight. So we've got two diagonal lines for cruise. And then we do have a diagonal line for takeoff. And for the most part, our vertical lines on the right side here, sea level 3, 5, and 7,000 feet, are being used for the takeoff. Otherwise, our percents here are being used for cruise flight. It's also entirely possible that you'll be given a brake horsepower setting. For example, question might say you got 200 brake horsepower used for takeoff and climb. What's the fuel flow if they have it for X number of minutes? So very, very straightforward chart. But keep in mind, this cruise lean is your best economy setting.